Welcome everybody to Algebra 2, Section 7.3, Intro to Logarithms and Properties of Logarithms. So first of all, what is a logarithm? A logarithm, often abbreviated to just log, is another way of writing exponents. And so we have this new logarithmic form, which would be read as log base b, which is very specifically written as a small b, and it is written lower, or what we call a subscript, of a equals x. And the same b, a, and x, the same logarithm written as an exponent or an exponential form would be b to the power of x equals a. And so how we go from one to the other is your b here is your base in your exponential form, and it is your base in your logarithmic form. And it's actually even literally called the base, log base b in the logarithmic form. And then we essentially, as I like to call it, spiral the exponent to the right-hand side of the equation to get the x on the other side, and then spiral the answer to the left-hand side, and that's what you're have the logarithm of. So your base is still your base. Then the exponent and what the right side of the equation are spiral with each other. And the same thing would be true whichever way you convert it. Your base stays your base. So as you go from logarithmic to exponential, your base is your base. And then your a goes to the right, your x goes to the left, and your x would be the exponent, and your a would be what it's equal to. So I like to think of this once again as a spiral. And so we're going to practice converting from first logarithmic to exponential form, and then we're going to go the other direction from exponential to logarithmic form. And then if we can simplify on these other conversions, we will. Actually, scratch that. We will not be focusing on any simplification. There will not be simplification needed. I'm getting ahead of myself. So number one, as we do this here, log base 3 of 9 equals 2 is how we read this. And once again, this 3 is our base, and it is written smaller and lower than everything else. Whereas 9 and 2 are just written as regular, normal-sized numbers. And so the 3 is still our base. We spiral the 2 over, and that becomes the exponent. We spiral the 9 over, and that's what it equals. And we can see this as a true statement. 3 squared does, in fact, equal 9. Number 2 here, 6 stays as our base. The 3 spirals over, and it's our exponent. The 16 spirals the other side, and it's what it's equal to. And 6 to the power of 3 is 216. Number 3, 7 to the power of 0 equals 1, because you spiral the 1 and 0 around, and that is a true statement. On number 4, 2 remains your base. You spiral the 4 over, and it's equal to 16, which is also a true statement. You'll notice that for each of these. Number 5 is 4 to the power of negative 2 equals 1 over 16. Quick reminder that negative exponents just tell you to reciprocate it. So 4 squared is 16. With a negative exponent, it makes it 1 over 16. Number 6 here, we have log base 9 to 27 equals 3 halves. So this is 9 to the power of 3 halves equals 27, which we may not initially think is, or initially know or recognize as a true statement, but it is. What this would end up being, if you're curious, is the square root of 9 to the third. And the square root of 9 would be 3, and so this would end up being 3 to the third, which is, yes, 27. You could also say 9 to the third, 729. Square root of that is 27, in case you're curious. Now we're going to go back the other direction. So we're going to convert from exponential form to logarithmic form. So we'll have log base 14. Whatever's being raised to a power is your base. We called it a base before. It's your base now as well. We're just saying base a little more forwardly. Then the 196 comes over, and so it's of 196 equals 2. So the logarithm is always equal to whatever the exponent would be. Once again, the logarithm is always equal to whatever the exponent would be. Number 8 here, 3 to the 4th equals 81. So as we do this, it's log base 3. Whatever's being raised to a power is always your base. Of 81, the answer is what it's logs of, and it's equal to your exponent 4. Once again, this follows a spiral with 4 and 81. On 9, 12, log base 12 rather, of 12 equals 1. Remembering that 1 is our exponent here, and 12 is what's being raised to the power. 10, 36, try that again, Mr. Kossel. Log base 36 of 6 equals 1/2. So once again, equal to your exponent, 1/2, which would be the square root, by the way. Number 11, log base 2 of 1/8 equals -3. And on number 12, log base 8 of 16 equals 4/3. So regardless of what numbers we had every time, we still followed the same pattern where our base became our base, whatever it was being raised to a power, and then our exponent and answer spiraled, switching sides. Moving on to the next page here, we're going to now evaluate some logarithms. But before that, let's talk about the common logarithm. A logarithm with base 10 is what we call a common logarithm, and it's often written without the base. So log base 10 of x is often just written as log of x. And this is because mathematicians are lazy, and since this is the most common base of logs that are worked with, it is just seen as the common one. And so when we don't write something, we just assume it's the most common version, which is 10, because mathematicians eventually got sick of writing it, and so they said, hey, we're just going to make it so if we don't write it, we'll assume it's a 10. Similar to how if you don't see an exponent on x, it's assumed to be a 1. If I don't see a coefficient in front of x squared, I assume the coefficient is 1. And if I don't see an index here inside, for a radical, then I assume that the index is 2. So in the exact same way, as each of those are assumptions that are made, this is also an assumption that is made that when we don't see a base for logarithm, that the base was 10. Now we're going to use our knowledge of exponents to evaluate the following logarithms. And so the question we're asking here is, what is the exponent that gets us from the base to the answer? And so it's helpful sometimes to think of this as it equals x, and then to do our spiral to turn it into exponential form, to where we have 7 to the power of x equals 49. And then we say, okay, what is that power of x? So I'm asking that same question, but it might be a little bit easier for us to see what's going on now that we can actually visually see where the exponent is, and that there is an exponent perhaps. So 7 to the power of 2 would be the answer. So our answer is 2. Now you don't technically have to put x equals 2 because there is no x. So the answer is just, quote, 2, because that's what the power of 7 to get to 49 would be. On number 14, essentially the question is, again, is 3 to what power is 27? But a way for some of us to help think about it, gives more structure, is to equal it to x. Spiral it, 3 to the power of x equals 27. It must be the power of 3. And if you write x equals 3 or 3, I don't care. They're both perfectly fine with me. Number 15, we don't see a base, so we assume it's 10. So it's 10 to what power is 100? Some of us might benefit from writing equals x, though, and writing 10 to the power of x equals 100. And the answer is 2. 10 squared is 100. One way to know that is it has 2 zeros. 10 to any power is just 1 with that many zeros. Number 16, 12 to what power is 1? Essentially, you set it equal to x. Spiral again. And x must be 0 in order for it to be 1, because anything to the power of 0 is 1. On number 17, we set it equal to x, and we get 2 to the power of x equals 64. Now, you might not know this offhand. It's not like 2 to the second or 2 to the third where we work with it more often. 2 to the blank equals 64 is not something we do often in Algebra 2. And so something that you can just do is in our calculator, just spam a bunch of different options. 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the sixth, 2 to the seventh, 2 to the eighth, until you find out which one is 64. The answer is that it'd be 6. 2 to the power of 6 is 64. Moving on to number 18. You get log base 3 of 243. And so we say this equals x. 3 to the power of x equals 243. And once again, the same idea where we just keep spamming 3 to a certain power, 3 to a certain power until we find out what it is. It would be the power of 5. There we go, kind of. Number 19. Set equal to x. 9 to the what power equals 1 over 81. And we say, oh, well, that's weird because it's 1 over something. Well, that must mean it's a negative exponent. So we know it'll be a negative, and then we just say 9 to what power is 81? And 9 to the second power is 81, so negative 2. On 20, 64 to the power of x equals, not x, but equals 4. This would be equal to x previously. And this is odd because normally the bigger number is on the right, because when we do exponents, normally we get a bigger number. But here we get a smaller number, and that's because it's a root of some sort. And remember, roots are exponents. And so we say, what root of 64 gets us 4? And once again, you can just spam a bunch of different ones in your calculator. Square root of 64, cube root of 64, fourth root of 64, fifth root of 64. Just keep trying until you find which one's 4. And it would be the third root. And so x wouldn't equal 3, but equal 1 over 3, which is the cube root. 1 over 4 is the fourth root, 1 over 5 is the fifth root, so on and so forth, as we've discussed. Next, we'll talk about the change of base formula. So some logarithms are not as easy to evaluate as ones above, because they're not a nice, clean power, essentially. It's not just like, oh, 2 to the power of 6 is 64, cut and dry. It may end up being something like number 21, where you have log base 16 of 64 equals x. And so if I were to set this equal to x, for example here, you would have 16, and I wouldn't write this down, but 16 to the power of x equals 64. And you could sit there for quite a while trying to figure this out, and you're probably going to be just kind of beating your head against the wall, unfortunately, to no avail, because it's not an integer that would do the trick here. It actually ends up being a fraction / decimal, depending on how you want to view it, and that does the trick. And finding that can be quite tricky. And so we're going to talk about what we can do to utilize our calculator in this instead of just continuing to beat our head against the wall. And so we have this thing called a change of base formula. And the reason this change of base formula is helpful is because we have a button on our calculator right next to the number 7 on these TI-84s, or on Calc 84. I'll showcase where it is as well. Once it loads, of course. Calc 84 is also right next to the 7. It just says log. And so if I tap log, that gives us log base 10 of whatever. And so I could do log base 10 of 100. And that means log base 10 of 100, or 10 to what power is 100? 2. I could do log base 10 of 1,000. And it's 3, because 10 to the power of 3 is 1,000. If I just keep adding zeros, it's going to just keep going up, because it's just another power of 10. And so I can evaluate that for any number. So I could do log base 10 of 22. And it gives me a crazy decimal here. And it even gave me as natural logs, which is interesting. I haven't seen that before on the calculator. But ignore that part of it and just look at the decimal, the 1 point, the which is, yes, a long decimal. And people just had to sit there and actually figure this out long ago. But we get the benefit of using a calculator because it's all programmed into it. And so once we have log base 10, we can just type it into our calculator. But what we need to do is turn that into log base 10, because 21 is log base 16, for example, not quite as helpful. And so we have this change of base formula, which turns it from any base into being logarithms with base 10. And so log base b of a, with b and a both being numbers, we would have log base a, sorry, not log base a, but log of a with a base of 10 over log of b with, once again, a base of 10. So now they are both common logs or common logarithms with a base of 10, and we can thus type them into our calculator. So we do the same thing on 21 here. So this ends up becoming log of 64 over log of 16. And then we would type this into our calculator in such a way. And so as you type it in, you have to be careful to end your parentheses before you divide. And what I mean by that, as I'll show it, is log of 64 parentheses divided by log of 16. And as I hit parentheses and hit enter, my calculator will tell me it is 1.5. And once again, ignore the ln, 64, all of that stuff. Instead, just look at the 1.5. That's what we need to be concerned about. And that would be our answer, because 16 to the power of 1.5 over 3 halves would do the trick. And so this simplifies to 1.5, which is our answer. Now, if I didn't put the parentheses in that problem, let's back up and see what happens. Log of 64 divided by log of 16. And I hit enter. The calculator thinks and thinks and thinks and thinks and thinks. I get a much different answer because my calculator thinks I'm doing something wildly different. My calculator thinks I'm dividing 64 by another logarithm rather than dividing two separate logarithms, because I never told my calculator I was done typing in my logarithm of what I was taking the logarithm of. Because when you type in log in your calculator, it's saying, oh, what are you taking the log of? And you have to put that in your parentheses. So that would be why the 64 needs to go in the parentheses, and the parentheses needs to end before dividing. So let's move on to other problems using this change of base formula. And so 22 would be log base 32 over log base 8, which then, as we just type this into our calculator, log base 32 divided by log base 8, we end up just getting 1.6 repeating. And a little helpful tip, the logarithm with the base is always going to be on the bottom. So notice 16 is on the bottom, 8's on the bottom, and 2 will also be on the bottom, 10 will be on the bottom. Every time the one with the base on the bottom will be on the, or one with the base will be on the bottom. Moving on to 23, this is log of 54 over log of 2, both base 10. And now if we type that into our calculator, we get to be approximately 5.75 if I round to 2 decimal places. On 24, this is log of 294 over log of 10, which if we round to 2 decimals is approximately 2.47. Now you may have noticed, and maybe you didn't, that this actually is base 10 already. So you could just simply type in log of 294 into your calculator and get this answer. Sorry, I should explain this further. The reason why this works to divide it by log of 10 as well, though, is because log of 10 is just 1. That's because log of 10, I'll write this off to the side over here, log of 10 is really log base 10 of 10, as we mentioned. And if I were to equal that to x, that's saying 10 to the power of x equals 10, which means it's 1. And so that logarithm just equals 1. And so on that last problem, we just did log of 294 divided by 1, aka not changing the result one bit. Moving on to number 25, log base 4 of 136. So this is log of 136 over log of 4, which the calculator tells me is approximately 3.54 rounded to 2 decimal places, the hundredth spot. Number 26, this would be log of 1 over 36 over log of 6. And the calculator will tell me that that's -2 on the nose, because 6 to the power of -2 would get you 1 over 36. The negative reciprocates it, and the 2 squares it to 36. Moving on to our next page, we're going to be talking about some products, or some properties rather. The first of which is the product property. The first of which is the product property. And so the product property, it says that log base b of m times n is the same thing as log base b of m plus log base b of n. You can separate it into two separate logs where the two logarithms are adding both have the same base of each factor. And it also works in reverse. And so on examples 1, 2, and 3 here, we're going to be condensing or doing that product property in, quote, reverse, where we're taking two separate logs, or you can even take 3 or 4 or 5 separate logs, and condense them into one single logarithm. And then on examples 4, 5, and 6, we're going to be taking a single logarithm and expanding it out to multiple logarithms. So, and then simplifying if possible on number 1, 2, and 3. So as we condense these are both log base 2. If they were different bases, we wouldn't be able to do anything with them, and the problem would just be done. But as it sits now, we can say since they're adding, that means what we're taking the log of is really multiplying together. That would serve as our m and n. So this becomes log base 2 of 7 times 4, 28. And we don't need to evaluate what this is. Simplifying and evaluating are different here. We are just condensing, and simplifying was actually multiplying 7 times 4. If I wanted to evaluate this logarithm, that's where we do the change of base and say, you know, log of 28 over log of 2, since 2 raised to a power would not give you 28, or 2 raised to an integer power would not give you 28. On number 2 here, they're both log base 10, common logarithm, which is good for them to be the same base. Otherwise, we couldn't do this. And so it's log base 10, or log of 100. And could you evaluate that, what that would be? Sure, it's 2, but we're not asked to do that here. We're just condensing. 3, since these are both log base 4, we can multiply what we're taking the log of in each of them. So log base 4 of 2x times 4x squared gives me 8x to the third. And that'd be my answer. On 4, 5, and 6, we're going to condense this, or excuse me, we're going to expand this out into separate logarithms. And so we have to say, okay, on number 4, for example, log base 10, or log of 6, log base 10 of 6, or log of 6, excuse me, we are saying, okay, what could 6 have multiplied from? What could have multiplied to get to 6? Well, for example, we could have done log of 2 plus log of 3, where 2 times 3 is 6. That would work. You could also do, 6 and 1, for example, if you wanted to. Those would be your two options. We're going to do the same thing here, log base 7 of 45. So we have to say what two numbers can multiply to get 45. Answers we'd be looking for are like 45 and 1, 5 and 9, and 15 and 3. I'm just going to do 5 and 9. So I'm going to do log base 7 of 5 plus log base 7 of 9. If you did 15 and 3, that's also perfectly fine, or other options, as I mentioned, like 45 and 1. On 6 here, we have two distinct parts. We have a 5 and an x, and that's what we're going to separate into two separate logarithms. And so we're going to do log base 2 of 5 plus log base 2 of x. And problems like this are going to be much more typical of expanding problems to where we can actually see two parts rather than on examples 4 and 5 where we just have to come up with factors of a number like 6 and 45. So once again, problems where we can actually see the two parts or the multiple parts is really what we're going to be seeing more often. And if there was a third part here, for example, of like 5xy, then we would just have a third logarithm plus log y, or log base 2 of y, rather. Moving on, our next property is a quotient property. So quotient means division. And so log base b of a quotient or of a fraction or of division, m divided by n, it can also expand into two logarithms. Log base b, the same base, of m minus the second log base b of n. So the same exact idea, except for now you're subtracting. And so if one logarithm is subtracting from the other or negative in front of it, that means it's going to be on the bottom of a fraction, whereas if one is positive, it'll be on the top of a fraction. That's a good way to think of it. 7, 8, and 9 will condense again. So on 7, since they're both log base 3, we can actually condense and get log base 3 of 24 divided by 8, or 3. On 8, since they're both 15s, we do log base 2 of 15 divided by 15, 1. And 9, log base 4 of x to the 9th minus log base 4 of x to the 2nd. So this ends up becoming, I'll show an in-between step here, log base 4 of x to the 9th over x squared. And we subtract those exponents. And so this becomes log base 4 of x to the 7th. Now we're going to go ahead and expand. And on number 10 and 11, we're going to have to kind of use our imagination to come up with things, whereas on 12 we see two distinct parts. Once again, number 12 is going to be much more typical of problems that we get. So on number 10 here, we say, okay, what could have divided to get us 4? And so literally there are infinitely many combinations. I'm going to put log base 8 of, I'll do 16 and 4. So I'm going to do log base 8 of 16 minus log base 8 of 4. What's important here is whatever numbers you pick the number that'd be on top of the fraction in that logarithm that has a positive at the beginning, essentially. You just don't see the plus sign. And you put the number that'd be on the denominator in the logarithm that has the negative in front of it. That is what's important here. On number 11, same idea. We'd say, okay, what could have simplified down to 1/3? And so I would say, oh, for example, it could be 5 and 15 or 6 and 18. Lots of different options. Once again, infinitely many. And so log of 5 I'll do a 6 and 18, I suppose. So 6 minus log of 5 of 18, log base 5 of 18. And so here it'd be important for the 6 to come first and 18 to come second because it's 1/3, and 6 divided by 18 is 1/3. On number 12 here, we can see the two distinct parts. So I'll do log of m minus log of 7 with the assumed base of 10. Next, we have the power property. So we're going to condense these, or excuse me, before condensing, we have to actually talk about the property. Log base b of m to the power of n, so an exponent inside the logarithm, means that the exponent is actually a coefficient, essentially, n times the logarithm of base b, or excuse me, logarithm base b of m. And so the exponent can just be moved back and forth between being a coefficient and being an exponent. So on 13, 14, 15, we will condense. So on 13, 5 times log base 4 of 2 is really log base 4 of 2 to the 5th. We put the 5 back in the exponent spot. And now we can actually do 2 to the 5th, so we will. That's our simplifying we'll do. Log base 4 of 32. We won't go any further, do any change of base or anything like that. Number 4 here, same thing. We'll put the 7 back as an exponent. Log base 2 of x to the 7th, and no more you can do there. On number 15, put the 1/3 back as an exponent. Log of 8 to the power of 1/3. And we can actually do 8 to the power of 1/3. It's a cube root of 8, and the cube root of 8 is 2. So it's log of 2. Now on 16, 17, 18, we'll be expanding these. And these we don't really have to use our imagination at all, actually, which is nice. So the 7 would come out as a coefficient, and so it'd be 7 times log base 2 of 8. And you can put the multiplication symbol. You don't have to. It's up to you. I often don't, personally. Number 17. We have a little bit of math to do here because there's already a coefficient out here. And so what we're going to do, and so as we bring this exponent of x minus 1 out in front, we'll have to multiply it with the existing coefficient, giving us 3 times the quantity of x minus 1 times log of 4. And so we'll distribute the 3, giving us 3x minus 3 in parentheses in front of log of 4. Now the reason we need that 3x minus 3 in parentheses is to emphasize that is all a coefficient of logarithm, not just the 3 or the negative 3 that is a coefficient. Number 17 here, log base 7 of the square root of w. Well, it might be helpful for some of us to write an in-between step here, that the square root of w is really w to the power of 1/2. Remember, the index or the root is the denominator, and the exponent is the numerator. So 1 over 2. And then now we'll have this as 1/2 times the logarithm of, log base 7 rather, of w. So now we're going to be condensing and simplifying. So we're going to be condensing using multiple properties. And so here on number 19, we'll be using this property for the power to move it, the coefficient to the exponent, and make it log of 6 squared minus log of 9. And then we'll actually square the 6 and get log of 36 minus log of 9. And then now we'll use the quotient property to say that, oh, this can actually be one singular logarithm if we divide 36 and 9, giving us log of 4. And that would be our answer. So we condense it into one singular log. We'll do the same thing on number 20, where this is log base 4 of a to the 4th plus log of base 4 of b squared, moving those coefficients as exponents. And then now we can write this as one singular logarithm by multiplying the a to the 4th and b squared, and get log base 4 of a to the 4th b squared. They don't actually combine any further because they're different variables. On 21, we'll have log base 4 of u to the power of 7 minus log base 4 of v to the power of 6. The existing exponent and the coefficient would multiply. And now we can write this as a singular logarithm, giving us log base 4 of u to the 7th divided by v to the 6th, which doesn't simplify further because they're different variables. On 22, with 3 different logs, any that are positive, which would be this one and this one, are on the top, multiplying together. Anything that are on the bottom, that are negative, like this one right here, are on the bottom. And so we end up having log base 2 of 60, 15 times 4, over 6. Because I just went ahead and multiplied these and then put that in the on the bottom and condense it into one singular logarithm. But we do have another step. 60 divided by 6 is 10. So this is log base 2 of 10. On 23, we have 3 separate logarithms all adding together. So we have like log base 3 of 4y, for example, but we actually have to put the 1/2 on this last one. And so it would be 4y times 49 to the power of 1/2 if I wanted to skip a step and go ahead and not write logarithm one more time. And then I actually have to square root 49, which is the power of 1/2. So that's log base 3 of 4y times 7. And I should clarify that all of this is inside the logarithm. So we don't think it's a times 7 at the end or after the logarithm. And then it's log base 3 of 28y. Which you could have initially just said this is 49 to the power of 1/2, or log base 3 of 49 to the power of 1/2, aka log base 3 of 7, and then multiplied 4 times y times 7, giving us 28y again, like we got. On 24, both these logs are going to be raised to the power of 1/3 individually, as we essentially distribute a 1/3 inside. And then this will be on the bottom of our fraction. And so we'll have log base 5 of 8 to the power of 1/3 times 27 to the power of 1/3 over 3. 8 to the power of 1/3 is 2. And 27 to the power of 1/3 is 3 cube roots. And then over 3. And that ends up being log base 5 of 6 over 3, which is log base 5 of 2. So I just kept simplifying as much as we could until we couldn't anymore. On to number 25, we end up having log base 2 of 4 cubed over 32. And then 4 cubed is 64, so log base 2 of 64 over 32, which simplifies further to log base 2 of 2. On 26, we have log of 6 squared over 16 to the 1/4. The negative means it's on the bottom. The 1/4 is really an exponent. And then this plus tells us that this one's on the top. And so we're going to have 6 squared times 3. And so this is log of 36 times 3 over the 4th root of 16, which is 2. And so that's log of 108 over 2, which is log of 54. Now we're going to expand these completely. So on 27, log base 6 of everything here. The parentheses are just telling us that all of that is inside the logarithm. And so we're going to make this 3 separate logs, each with base 6. Log base 6 of x plus, because it's multiplying, log base 6 of y plus 4 times log base 6 of z. Now we had to bring this 4 out in front as the coefficient for that last part to fully expand this. If you left it as z to the 4th, then it would not be fully expanded. And so 28, we're going to have 2 separate logarithms with a minus sign in the middle, one for the a and one for the b, and 9 will be a coefficient. So we'll have 9 times log base 4 of a minus log base 4 of b as our answer, and that's fully expanded. 29. Before anything else, I'm going to actually multiply this exponent inside of these other exponents to make my life easier by simplifying this. So I'll get log base 7 of q to the 8th r to the 4th as those exponents multiply. Now I'll expand this into 2 separate logarithms, each with their own coefficient, that is their exponent. So we'll have 8 times log base 7 of q plus 4 times log base 7 of r. On number 30, I'll do the same thing where I have this exponent outside and I distribute to each exponent inside, giving me log base 2 of y squared over z to the 10th. And now as I separate this into two separate logs, 2 times log base 2 of y minus 10 times log base 2 of z. It might be helpful to write each of these as their own individual power before proceeding. Log of 7 to the power of 1/2 and x to the power of 3/2. Remembering that the index is your denominator for an exponent, and the numerator is your power, or your exponent currently. And so now we'll make this two separate logarithms, 1/2 times log of 7 plus 3/2 times log of 3/2. Times log of x rather. Number 32, I'll do the same thing where I make this individual exponents. So log base 3 of m to the power of 5 over 4, and then to the power of 2 over 4, which simplifies to 1/2. And so now as I make this two separate logs, I'll do 5/4 times log base 3 of m plus 1/2 times log base 3 of n. And now for a nice little graphic organizer. So this will cover all 5 of the different things main things we covered today: the basic logarithm, the product rule, the quotient rule, the power rule, the change of base formula, and then what common logarithms are, that it's just base 10. You just don't see it. And then some examples of each so we can actually see what's going on. So basic logarithms, log base b of b is just 1. That's just saying essentially b to the power of 1 equals b, because we're always saying what power is it raised to essentially. What power do we raise a base to get what we have the log of? And so if you have the base and this number are the same, the answer is 1. And then log base b of 1 is always going to be 0, because that's saying b to some b to the power of 0 would equal 1, and anything to the power of 0 is always 1. So that's just always going to be the case, that if you have, once again, any scenario where it's log base b of b, those two numbers are the same, the answer is 1. And then if you have log base b of 1, the answer would be 0. So practicing this, log base 14 of 14, we're saying 14 to what power is 14? The answer is 1. Example 2, log base 3 of 1, we're saying 3 to what power is 1? The answer is 0. Remember, that'd be like 3 to the power of x equals 1, and 14 to the power of x equals 14, for example. Product rule. Log base b of m times n is the same thing as log base b of m plus log base b of n. Two separate logs, you can expand that out or condense it depending on which way you go. So we'll do one of each. So the condensing, log base 5 of 6 plus log base 5 of 7, we would do log base 5 of 6 times 7, or 42. Log base 2 of 63, we can expand this by saying what times what would get 63. There's 21 and 3, there's 9 and 7, for example. I'll do 9 and 7. So I'll do log base 2 of 7 plus log base 2 of 9. If you did 9 then 7, that's fine. If you did 21 and 3, 3 and 21, that's all fine as well. The quotient rule is the same idea, but now we're dividing. And so instead of adding the two separate logarithms, we will be subtracting the two logarithms, with the one with a minus sign being on the bottom of our fraction. So as we condense, this would be log base 4 of whatever 84 divided by 12 is, which is 7. Or as we expand, we say what could have divided to get to 9? Literally infinitely many examples. I'll do 27 divided by 3. So I'll have log of 27 minus log of 3, both being base 10, since our original was base 10. The power rule, log base b of m to the power of n. We bring this exponent out in front as a coefficient, so n times log base b of m. So condensing, make 2 the exponent, log base 3 of 8 squared, which really is log base 3 of 64. And then if you expand, we have this x minus 1 out in front as a coefficient, but in parentheses, because it's all a coefficient, and we need to emphasize that, times log base 2 of 6. And last but not least, the change of base formula. Log base b of a is the same thing as log of a over log of b, allowing us to use log base 10 in our calculator for problems like this. And so in order to evaluate this on a calculator, we say this is really log base or log of 32 over log of 7, both base 10. And then our calculator will tell us this is approximately 1.78, rounded to 2 decimal places. And once again, a quick reminder at the bottom that base 10 logs are common logs and are written without the base, most often log of x. If you write it with the 10 there, it's not wrong, just uncommon.